In an era increasingly shaped by artificial intelligence, large language models, or LLMs, stand at the forefront. Tools like ChatGPT have captivated the world with their ability to generate human-like text, answer complex questions, and even engage in creative writing. To many, their capabilities seem almost magical, a leap forward in our interaction with technology. But what truly lies beneath this impressive facade? How do these sophisticated systems actually work, and what makes them so powerful yet simultaneously constrained? This is a journey into the heart of LLMs. Our aim is to peel back the layers of complexity and demystify the core mechanisms that power these fascinating digital entities. We'll explore the entire pipeline, from the foundational data collection to the intricate neural networks that process information. The goal is to make this complex subject accessible to a general audience, transforming abstract concepts into understandable insights, much like Andrej Karpathy's deep dive video, which offers a goldmine of information for those seeking clarity. Building something as sophisticated as ChatGPT isn't a simple task. It's a multi-stage process involving immense computational power and vast datasets. This complex pre-training process is the bedrock upon which all LLMs are built. It begins with the fundamental act of collecting and processing gargantuan quantities of data, a step that lays the groundwork for the model's eventual understanding and generation of human language. This initial phase alone is a monumental undertaking, defining the very potential of the AI. The journey of an LLM, from raw data to a conversational AI, follows a well-defined pipeline. It typically involves three critical stages: pre-training, fine-tuning, and reinforcement learning. Each stage builds upon the last, progressively refining the model's abilities. This systematic approach ensures that the LLM not only learns to process and generate human-like text but also aligns its responses with human preferences and instructions, making it a truly useful and interactive tool for a wide range of applications. The initial and most resource-intensive phase is pre-training. This is where the model is exposed to an unprecedented volume of text data, essentially learning the structure, grammar, semantics, and nuances of human language. This data is downloaded and processed from across the internet, encompassing books, articles, websites, and more. It's akin to a child reading every book in a library simultaneously, absorbing all human knowledge to understand how words and ideas connect. Without this foundational knowledge, no sophisticated interaction is possible. Before any language model can process text, it must first convert words and subword units into a numerical format it can understand. This process is called tokenization. Imagine taking a sentence and breaking it down into its smallest meaningful components, or tokens. These tokens are then assigned unique numerical identifiers. It's the essential first step in translating the fluid, expressive nature of human language into the precise, mathematical world of a computer, making it ready for processing by neural networks. The journey from words to bits is a fundamental concept in computing. Initially, every character, every word, can be represented as a sequence of ones and zeros. This binary representation, however, can be incredibly long and inefficient for language. To make it more manageable, these bits are grouped into bytes, typically 8 bits, forming 256 different possible combinations, from 0 to 255. This significantly shortens the sequence, allowing for more efficient processing, a crucial optimization in handling vast quantities of text data. At the core of every LLM lies a neural network, a complex system inspired by the human brain. These networks consist of interconnected layers of neurons that process information. They don't just store data, they learn patterns, relationships, and context from the vast datasets they're trained on. The magic, as it were, is in their ability to identify subtle connections and make predictions, transforming input tokens into meaningful outputs. This intricate web of computations is what allows LLMs to understand and generate language. While many types of neural networks exist, large language models predominantly use a specific architecture known as the transformer network. This innovative design, introduced in 2017, revolutionized natural language processing. The transformer's key strength lies in its attention mechanisms, which allow it to weigh the importance of different words in a sentence, regardless of their position. This ability to understand long-range dependencies is what enables LLMs to grasp context and generate coherent, relevant responses. The magic of LLMs is often described as complex mathematical expressions. Within the transformer network, tokens are processed through multiple layers, each performing intricate operations. At its heart, these operations involve numerous matrix multiplications, the computational engine that transforms raw numerical data into contextual representations. This continuous, iterative mathematical processing allows the model to refine its understanding and generate increasingly accurate and nuanced predictions, turning abstract numbers into meaningful language. During pre-training, the LLM is given a vast amount of text and its primary task is surprisingly simple: predict the next word, or token, in a sequence. By repeatedly guessing the next token and adjusting its internal parameters based on how right or wrong it was, the model learns the statistical relationships between words. This seemingly straightforward objective, applied across internet-scale datasets, is what imbues the LLM with its profound ability to generate coherent and contextually appropriate language, piece by piece. After the extensive pre-training phase, the LLM is a generalist, capable of generating text but not yet optimized for specific tasks or polite conversation. This is where fine-tuning comes in. The model is trained on smaller, more specific datasets that reflect desired behaviors, such as answering questions, summarizing text, or following instructions. This stage refines the model's responses, making them more useful and aligned with human expectations, transforming a broad language learner into a more specialized, helpful assistant. The final stage for models like ChatGPT often involves reinforcement learning with human feedback, or RLHF. In this process, human evaluators rank the quality of different responses generated by the model. This feedback is then used to further train the LLM, teaching it to produce answers that are not only factually correct but also helpful, harmless, and aligned with human values. RLHF is crucial for giving LLMs their polite, conversational tone and ensuring they meet ethical guidelines, bridging the gap between raw AI and user-friendly interaction. Behind every seamless AI interaction lies an immense demand for computational resources. The training and inference of LLMs require staggering amounts of processing power, particularly from graphics processing units, or GPUs. These specialized chips are adept at parallel processing, performing many calculations simultaneously, a necessity for the matrix multiplications inherent in neural networks. Without this sophisticated hardware, the scale and speed of LLM operations simply wouldn't be possible, highlighting the physical infrastructure behind digital magic. The insatiable demand for computational power has led to what many call a gold rush for GPUs. Companies like NVIDIA, which produce these powerful chips, have seen their value skyrocket. This isn't just a technological trend, it's an economic phenomenon. The core message here is that the seemingly magical abilities of LLMs are deeply reliant on incredibly expensive hardware and vast data centers. These facilities are specifically dedicated to the continuous process of next token prediction, working tirelessly with internet-scale datasets. The sheer volume of data involved in training LLMs is almost unfathomable. These are not small, curated collections, they are internet-scale datasets, comprising trillions of words gathered from the vast expanse of the web. This includes everything from published books and academic papers to casual conversations on forums and social media. Processing such quantities requires not only immense storage but also sophisticated algorithms to clean, filter, and organize the information, ensuring the model learns from reliable and diverse sources. In the world of AI, certain voices cut through the noise with unparalleled clarity. Andrej Karpathy, a renowned expert, is one such individual. His detailed explanations on platforms like YouTube and X are consistently hailed as a goldmine of information. His latest video, a deep dive into LLMs like ChatGPT, offers an in-depth breakdown of the key mechanisms behind these models. For anyone seeking to genuinely understand the nuts and bolts of how LLMs operate, Karpathy's work is an invaluable resource, providing context and technical depth. Karpathy's work is more than just a technical explanation, it's a guide to understanding the very psychology of these machine minds. He delves into how they are developed and even offers mental models for how to interpret their behavior and limitations. While his deep dive is extensive, running over 3 hours, its length is a testament to the complexity of the subject matter. It reinforces that truly grasping LLMs requires patience and a willingness to explore the intricate details of their design and function, moving beyond superficial explanations. At its heart, LLM training revolves around core principles of statistical learning and pattern recognition. The model doesn't understand language in the human sense, rather, it identifies intricate statistical correlations within the vast text it consumes. During inference, these learned patterns are leveraged to generate new text that is statistically probable to follow a given prompt. This seemingly simple mechanism, scaled to an unprecedented degree, is what allows LLMs to produce creative, coherent, and contextually appropriate responses, mimicking human intelligence. Despite their incredible capabilities, LLMs are not without their challenges and limitations. They can sometimes hallucinate, generating factually incorrect or nonsensical information with high confidence. Bias present in their training data can also be reflected in their outputs, leading to unfair or prejudiced responses. Furthermore, their reasoning abilities, while impressive, are often superficial, lacking true understanding or common sense. Recognizing these constraints is crucial for responsibly using and developing these powerful tools. The journey from words to bits, through bytes, and then through complex neural networks, is a testament to human ingenuity. It's a process that converts abstract human language into a form that machines can manipulate, learn from, and ultimately, generate. This intricate dance between human creation and machine processing is what defines the current frontier of artificial intelligence, allowing us to build systems that can interact with us in profoundly new ways. The deeper we dive, the more we appreciate the subtle elegance of this conversion. One of the most intuitive and powerful applications of LLMs is language translation. By being clever with prompts, users can leverage an LLM's inherent understanding of multiple languages to create highly effective translation tools. For example, simply instructing the model to act as an English-Korean translator app and providing a few examples of input-output pairs can enable robust, in-context translation, demonstrating the immediate utility and versatility of these models beyond simple chatbots. This method of giving the model a few examples to guide its behavior is known as few-shot prompting. Instead of extensive retraining, you provide a prompt that effectively programs the LLM for a specific task. For instance, to build a Q&A assistant, you might provide a prompt with examples of questions and their desired answers. This leverages the model's in-context learning ability, allowing it to adapt to new tasks rapidly without needing a dedicated training phase, showcasing its remarkable flexibility. The in-context learning ability of LLMs is one of their most impressive features. It means the model can learn from the information provided within the prompt itself, without requiring any updates to its underlying neural network weights. This allows for dynamic, on-the-fly adaptation to new instructions or data, making LLMs incredibly versatile. It's like having a highly intelligent assistant who grasps new rules and preferences simply by observing a few examples, showcasing a sophisticated form of intelligence. Beyond translation, LLMs excel as intelligent assistants. By crafting a prompt that defines a specific persona and task, you can create an assistant that answers questions, generates creative content, or even debugs code. The key is to structure the prompt effectively, providing clear instructions and any necessary context. This ability to embody different roles and perform diverse functions through simple text prompts underscores the immense potential of LLMs to augment human productivity and creativity across countless domains. The intense computational demand has ignited a gold rush for powerful GPUs. Companies like NVIDIA, at the forefront of this hardware revolution, have seen unprecedented growth. This economic ripple effect highlights that the so-called magic of LLMs is deeply intertwined with tangible, expensive hardware and vast data centers. These facilities are purpose-built to execute the continuous, resource-intensive task of next token prediction, operating on colossal datasets gathered from the Internet's farthest reaches. The digital frontier is built on very real, physical infrastructure. The economic impact of LLMs extends far beyond just GPU manufacturers. The need for specialized AI talent, the development of new software frameworks, and the burgeoning market for AI-powered applications are reshaping industries globally. From startups to tech giants, companies are investing heavily in LLM research and deployment, transforming business communication with tools like DeepL-Ari's translation and voice services. This investment signifies a long-term commitment to integrating advanced AI into every facet of our digital lives, driving innovation and competition. What does the future hold for LLMs? We are likely to see continued advancements in efficiency, accuracy, and safety. Models will become even more capable of understanding complex instructions and generating nuanced, context-aware responses. New architectures and training methodologies will emerge, pushing the boundaries of what's possible. The integration of LLMs into everyday tools and services will only deepen, making intelligent assistants a ubiquitous part of our digital existence, fundamentally changing how we interact with information and technology. While our focus has been on text-based LLMs, the frontier is rapidly expanding into multimodal models. These advanced systems are capable of processing and generating not just text, but also images, audio, and video. Imagine an LLM that can describe a complex image, create music from a textual prompt, or even generate a short video clip based on your description. This evolution promises to unlock entirely new dimensions of human-computer interaction, making AI agents even more versatile and intuitive. Despite the machine's complexity, the human element remains paramount. From the data scientists who curate datasets to the engineers who design neural networks, and the ethicists who guide AI development, human intelligence and values are embedded throughout the LLM pipeline. Reinforcement learning with human feedback underscores this symbiotic relationship, ensuring that these powerful tools serve humanity beneficially. The future of LLMs is not just about technological advancement, but about responsible co-evolution with human needs and aspirations. An insightful perspective views LLMs as a blind machine exceptionally skilled at pattern recognition and prediction, but without genuine understanding or consciousness. This blindness is why their magic needs careful guidance, often through clever prompts and human oversight. They process tokens, perform mathematical operations, and generate statistically probable sequences, but they don't think or feel in the way humans do. This mental model helps to manage expectations and understand the true nature of their intelligence. A fascinating aspect of LLMs is their ability to interpret and learn from unannotated datasets. Unlike traditional machine learning, where data often requires painstaking human labeling, LLMs can infer patterns and relationships from raw, unstructured text. This self-supervised learning significantly reduces the human effort required for data preparation, allowing models to scale to truly internet-sized proportions. It's a testament to the power of simply letting a vast neural network read everything it can get its digital hands on. Ironically, LLMs are not just tools for generating language, they are also proving invaluable for analyzing it. Researchers are leveraging LLMs to understand how humans use language, identify subtle biases, and even map the evolution of linguistic patterns. By providing sophisticated capabilities for parsing, summarizing, and contextualizing vast amounts of text, LLMs improve human language analysis in fields from linguistics to social sciences. They are both creators and analyzers, offering new lenses through which to examine our own communication. The reach of LLMs extends far beyond text generation into critical scientific fields, notably drug discovery. By rapidly analyzing vast quantities of scientific literature, chemical compounds, and biological data, LLMs can identify potential drug candidates, predict their efficacy, and even simulate molecular interactions. This significantly accelerates the typically slow and expensive drug development process, offering hope for faster breakthroughs in medicine. The ability to process complex, interdisciplinary data makes LLMs transformative for scientific research. From the surface-level interaction with ChatGPT to the deep internal workings of transformer networks and matrix multiplications, we've journeyed through the intricate landscape of LLMs. What once seemed like magic is now revealed as a complex, yet understandable, feat of engineering, data science, and computational power. The power of these tools lies not in any mystical quality, but in their meticulously designed architecture and the sheer scale of the data and resources dedicated to their training. As we conclude our deep dive, it's clear that large language models are not just a passing trend but a foundational technology with far-reaching implications. Their continued evolution promises to reshape industries, redefine human-computer interaction, and unlock new frontiers of knowledge and creativity. By understanding how they work, we are better equipped to navigate this evolving landscape, harness their potential responsibly, and contribute to a future where AI serves as a powerful and beneficial extension of human capability.